Hi everyone. The plan for today is to have a short introduction to logistic regression. Logistic regression is a machine learning method that can be used to solve classification problems. We already know another algorithm for classification, the naive Bayes algorithm. If X denotes the input and Y denotes the class label or target label or output, and Y given X is the conditional distribution of this target label conditioned on the input X, then we already know that the optimal classifier is this function f star x, which just selects the class label Y where this conditional distribution has its maximum value. As we already discussed, the naive Bayes assumption assumes that the input features become conditionally independent when we condition on the target label Y. Based on this, the naive Bayes classifier decision function is just this expression here. We want to find the target label Y where this function has its maximum value. As we also discussed, the naive Bayes classifier assumes that there's a simple parametric form of Px given y and Py distributions, and these parameters can be found with maximum likelihood or maximum a posteriori estimation. So to summarize, naive Bayes classifiers assume some kind of forms for the joint distribution of input x and output y. In practice, it's done by assuming a parametric distribution for px given y and py, and then we estimate the parameters of these distributions directly from the training data. Those algorithms that create an estimate of the joint distribution Pxy are called generative methods. Another class of algorithms argues that in order to solve classification or regression problems, it's enough to estimate Py given x, and we don't need to estimate the full joint distribution. These algorithms called discriminative methods. Logistic regression is one such discriminative method for classification problems. It's important to mention that although this method is called regression, it is actually an algorithm for classification. To summarize the most important points of logistic regression, logistic regression assumes some kind of functional form of the decision boundary. It estimates the parameters of Py given x directly from the training data, and it ignores learning the distribution of Px completely. To start the discussion of logistic regression with a simple problem, let's assume that the class label y can have two different values only, either 0 or 1. So this is a binary classification problem. We also assume that input x is a d-dimensional real vector. Logistic regression assumes that the probability that the class label y is 1 given the d-dimensional input vector x is given in the following specific parametric form. It is 1 divided by 1 plus exponential this expression, where this expression is just the linear combination of d components of the d-dimensional input feature x. The coefficients of this linear combination are w1, w2, and so on, wd, and we also often add w0, which is a so-called bias term. It's easy to see that this expression is non-negative and smaller than 1. If we already know what the probability of p y equals 1 given x is, then of course we also know the probability that y is 0 given x, because the sum of these two terms has to be 1. The probability that y is 0 given x is just this expression here. The decision function is therefore nothing else, just a logistic function applied to a linear combination of the input feature vectors. Therefore, the name of this classification method is logistic regression. Although the decision function of logistic regression is a nonlinear function in X, it's interesting to observe that this logistic regression is actually a linear classifier. That is, the decision boundary between the two classes is linear. How can we see this? First, we need to calculate the probability that the class label is 0 given X, and the probability that the class label is 1 given X. Then we calculate the ratio of these two numbers. If this ratio is bigger than 1, it means that the predicted class label is 0, and when this ratio is less than 1, it means that the predicted class label should be 1. When we calculate this ratio, we can see that it's actually just an exponential function, and inside this exponential function there is this linear function. We want to know when this expression is bigger than 1 and when it is less than 1. If we take the logarithm, then we just need to see when this expression is bigger than 0 and when this is less than 0. But what we got is just a linear expression, so we just need to check when this linear expression is less than 0 and when it's bigger than 0. To visualize this decision boundary, we just have to solve this equation and find a solution when this linear combination is 0. For those x features, when this linear combination is bigger than 0, the predicted class label will be 0, otherwise the predicted class label will be 1. That's all great, but you might wonder how we can generalize this to more than 2 classes. It's actually very easy. If we have capital K different classes and the features are d-dimensional, then for each feature I and class label K, we can introduce a parameter wki. For this class K, we also introduce an extra parameter wk0, which is called the bias parameter. With logistic regression, the probability that the class label y is yk, given the input vector x, is just this expression here. We use these probabilities for class labels y1, y2, and so on, yk-1. And for the last one, for the yk class label, we use this other expression here. As you can see, these numbers are valid probabilities for the class labels because they are non-negative, and if you sum all these capital K probabilities, you would get 1. At this point, I would like to ask you to think for a minute and try to figure it out if the decision boundary among the K different classes is still linear. So now that we know what logistic regression is, we still have one task left, namely we still have to see how to train logistic regression and how to find the best W parameters using our training set. To keep everything simple, let's just assume that we are dealing again with binary classification. We only have two classes where y could be either 0 or 1. This is the probability that y is 0 given x, and this is the probability that y is 1 given x. We have a training data set given as x1, y1, x2, y2, and so on, x and y in pairs, and the input x is a d-dimensional vector. We want to find the best parameters w. To achieve this goal, we can try to do maximum likelihood estimation. Here, we would need to maximize the probability of the training set in w parameters. The problem is that we don't have a joint distribution of x and y. As we discussed, this time we don't want a generative model. We only want to create a discriminative model where we only need to model the probability of y given x. The solution is to use a maximum conditional likelihood estimate instead of a maximum likelihood estimate. That is, we want to find that w that maximizes the probability of y given x. So we need to calculate the conditional likelihood function, and then we need to maximize that in parameter w. Calculating this conditional likelihood function is very easy. We assumed that the instances in the training set are IID, that is, they are independent and identically distributed. Because of this assumption, the conditional likelihood is just the product of these p y given x probabilities in the training set. To simplify the calculations, after creating this product, we take the logarithm of this quantity, and then it's very easy to see that our objective that we need to maximize in w will have this very nice and simple form. Alright, so this is what we need to maximize in w. The good news is that this function is concave in w, and because of that, the locally optimal solutions are globally optimal as well. The bad news is that we cannot find a closed form solution to this problem. Usually, the way to find closed form solutions is to calculate the derivative of the objective function and solve that when that derivative is 0. In our case, however, we cannot do that. Luckily, however, concave functions are easy to optimize. Alright, so when we have a concave function and we want to maximize it, or when we have a convex function and we want to minimize it, we just need to calculate the gradient and then do gradient ascent on a concave function or do gradient descent on a convex function. I'm just visualizing here the gradient descent on a convex function. We start from this point, we calculate the gradient, and then we move to the direction of the negative gradient to minimize this function as quickly as possible. The gradient descent is an iterative method. We fix a positive learning rate eta, and then the W parameters in the next iteration t+1 are updated as the parameters in the current iteration t minus the learning rate eta times the gradient in the most recent point. You can prove that this method will converge to a global minimum point of the convex function. And that's all for now. As you can see, logistic regression is a very simple method. You often can get very good results with it, and it's very popular, and I also recommend you give it a try and see when you can get good results with it. Thank you for your attention.